Okay, guys. I thought it would be a good idea to introduce the next part of our balancing equation unit by sort of narrating this set of notes that I'm about to show you here. This set of notes is all about reaction types. So we've had a lot of practice with balancing equations these last few weeks, and hopefully this will allow us to transition into actually categorizing these reactions. What you see here is an example of each of the 5 different types of reactions. Up here on the upper left is an example of a combustion reaction, a match burning. In the middle here, we see an example of baking soda, which decomposes or breaks down when you heat it, and that's what creates the bubbles of carbon dioxide that allow breads to rise or cookies to rise. And over here we see a tank full of ammonia, which is made by a synthesis reaction where you put nitrogen and hydrogen together. Here we have a single replacement reaction where you see copper wire reacting with a magnesium compound. The blue that you see is some of the copper dissolving into the solution. And then we see a double replacement reaction in which 2 solutions, 2 clear liquids, come together to form this yellow solid right here that's going to settle at the bottom of the test tube. So, without further ado, let's go ahead and get going here. So, like I said, now that you've had some practice with balancing equations, and I'm going to put this back up in a minute, I just wanted to make sure things were going well, it's time to categorize each of these reactions by their type. So, like I said, every reaction we're going to study falls into one of 5 categories: synthesis, decomposition, combustion, single replacement, or double replacement. And you're going to find that you already know a lot of examples of these reactions that you're going to be able to use in this class. Okay, so just before we get into the different types, here are some reminders. So like we talked about in class these last few weeks, there are 7 diatomic elements, and diatomic means 2 atoms that are doubled up when they're by themselves. So if you see them by themselves in a reaction that is without another element in a compound, they're going to be written as you see on the screen. So hydrogen is H2, nitrogen is N2, oxygen is O2, fluorine is F2, chlorine is Cl2, bromine is Br2, and iodine is I2. So you can see that actually 6 of these 7 form the number 7 here on the right side of the periodic table. And if they're in a compound, you got to find the formula as you normally would. And you might see some state symbols in these reactions, and they can actually really matter here. S stands for solid, L stands for liquid, G stands for gas, and AQ stands for an aqueous solution. You're actually going to see a lot of those, and that's one in which an ionic compound is dissolved in water. So let's get on with these reactions. So the first one is a synthesis reaction. And in a synthesis reaction, we have 2 elements in their natural states combining to form a compound. And a great example is found in a hydrogen fuel cell, and that's used to run some environmentally friendly cars, and increasingly, a lot of bus fleets are actually using hydrogen fuel cells to run completely clean buses. This is actually one in Boston. You can see the T there. So the MBTA runs hydrogen fuel cell buses within the city limits. And you can see that the reaction that's happening inside that fuel cell is just hydrogen combining with oxygen to form water. And again, the cool thing about this is that instead of all the exhaust fumes that get emitted from a car, because we know that cars are a huge source of greenhouse gases and other sources of pollution, hydrogen fuel cells only produce water as their exhaust. In fact, I've seen videos where literally someone will take a hydrogen fuel cell car, put a glass underneath, collect the water, and drink it. It's just water. And so if we can, make that technology cheaper and easier to use, we could run clean fuel with all of our vehicles. It'd be great. So, synthesis involves putting 2 elements together to form a compound. Decomposition is basically exactly the opposite. So, whereas in a synthesis reaction we end up with 1 product, in a decomposition reaction we end up with 1 reactant. That reactant, here it is baking soda or sodium hydrogen carbonate, breaks down to form 2 or more smaller substances. Often these are elements. In this case, they're small compounds. And so this reaction that you see here is what happens when you add baking soda to cake batter and you begin to bake it. This is sodium hydrogen carbonate, or sodium bicarbonate, you may hear it called. And it breaks down when it's heated without any other reactants to form three compounds: sodium carbonate, CO2, which is the bubbles that you see in cake batter, and water, which just evaporates into the air in that 350, 400 degree oven. So again, decomposition and synthesis are basically opposites of each other. Synthesis reactions involve elements coming together to form one compound, so they'll have one product on the right, and decomposition reactions involve one reactant breaking down, usually with the input of energy, like heat, to form one or more products. So now let's go to the fun one. This is the one you always want to see. So, we've burnt stuff in class this year, and we will again, don't worry. And I figure the weather's getting warm, it's getting towards spring, and you're going to want to have some friends over, if you can do so safely, for some burgers on the grill. You can just sit 6 feet apart and have a barbecue. And a lot of your grills are going to run on propane, and we've actually gone over this reaction a number of times where propane is burned in oxygen to form two products. So anytime you burn a compound like this, you can see that this compound has carbon and hydrogen. So we call it a hydrocarbon. There's a whole class of compounds which are derived from crude oil, which is the stuff you dig up from under the earth. And when we burn those things in oxygen, like you see here, we're always going to form the same two products: carbon dioxide and water. So if we form these two products, and if the thing on the other side, on the reactant side on the left, has carbon and hydrogen, then you can be pretty sure it's a combustion reaction. Combustion is just a fancy word for burning. The thing that I would really look for here is the presence of oxygen there, O2 as a reactant, because obviously you need air to burn things, and oxygen is the part of air that actually allows things to burn. Okay, so just for an example from my past, what you're looking at here is a Jiko. And a Jiko is a pretty common small charcoal grill that they would use in Africa quite a bit. I actually had a Jiko in my home in Kenya. I didn't use it that much because it's a little more tedious to set up, but a lot of people didn't have access to propane. It was very expensive, and so they would grill with charcoal. You can actually make charcoal really easily by burning wood very slowly under a pile of dirt, basically. Like, you light wood on fire and you cover it with dirt so that just a little air gets in, and it burns so slowly that it eventually forms charcoal. Now, when you burn charcoal, all you're doing is taking carbon and you're breaking it down in the presence of oxygen. So you're combining carbon and oxygen, you're burning carbon to form CO2. In this case, charcoal is just pure carbon. So this is another example of a combustion reaction. And so what I'm going to do is I'm actually going to film a separate video that walks you through the balanced equation that you would go through when you're burning gasoline in your car. The major component of gasoline is octane, and so that's a bit of a tricky combustion equation to balance that I'm going to walk you through in a separate video. So stay tuned for that. So now we have a single replacement reaction, and a single replacement reaction is one in which you have an element and a compound, and one element replaces another in that compound. Usually, you're going to see something like this, where you have one metal that's by itself. Here we have magnesium. And we have another metal that's part of a compound. Here we have copper. And when those two combine, the element that was by itself essentially replaces the other one in the compound. So you end up with those two metals switching places. We have magnesium nitrate, which is a compound, and we have copper, which is an element that's by itself. So if you were to do this in the lab, you would notice that it would start out as kind of a blue color, which would be caused by the copper, and then you would start to see that blue color start to fade as the copper turned into solid. And so you'd see that sort of copper-colored metal start to form on the edge of the magnesium. Now, this is all very dependent on what we call the activity series, which we're going to introduce in a minute. But long story short, if the metal in the compound is more reactive than the one that's by itself, then nothing happens. Those metals that are really reactive want to be with other elements. and want to be with other elements in a compound. And so if that's the case, then no reaction occurs. So I'm going to go ahead and move right on to that. Please forgive any barking you might hear in the background. My puppy is very sad to not be part of the walking outside. And so what we're looking at here is called the activity series. And I'm just going to double check here that we still have plenty of time. So the activity series here, it governs whether or not reactions between metals are going to happen. The ones at the top are most reactive, and when they're by themselves, they're going to tend to react to remove less reactive metals from their compounds. You'll notice here that magnesium is way above copper, so when it's by itself, it's going to kick copper out and make that reaction happen. Okay, so another situation where you might see single replacement is with halogens. The pattern's really easy. Basically, if you have a halogen that is above another on the periodic table, and it's by itself, because you can see here in these equations that fluorine and chlorine are by themselves. They're diatomic, but they're still just one element. They are going to replace less reactive or lower halogens. So if we have fluorine trying to replace chlorine in this compound, in sodium chloride, it's going to happen because fluorine is more reactive. And fluorine, because it's more reactive, wants to be part of a compound rather than by itself. If we try to go the other way and chlorine tries to replace fluorine, then there's not going to be any reaction at all. And so the reactivity goes basically down the group. Okay, so last type of reaction here is double replacement reactions. And I'm going to put this up on the big screen so everybody can see. So in a double replacement reaction, we have two ionic compounds in aqueous solution. That means that we have ionic compounds dissolved in water, and they react together to form different products. This basically involves the ion switching places. You can think of this like different dance partners. When you all had to awkwardly square dance in elementary school, you kind of know what I'm talking about here. And they have to involve a change in physical state. So something on the right side of the equation in the products has to be a solid, liquid, or gas. So one type is neutralization. When acids and bases react, they neutralize each other. And acids are going to react with bases to form a salt, which is just an ionic compound, and liquid water. So Mylanta down here was actually a thing that was used a lot in the past and still is available to neutralize stomach acid. And the stomach acid that we have in our stomachs is hydrochloric acid, and it reacts with magnesium hydroxide, as you can see down at the bottom of the screen here, to form magnesium chloride and, like I said, water. So again, we have that state change here where we have something that's a liquid on the right side of the equation. And we can see that the ions switched places. Okay, another example here is precipitation. Now, when we think of precipitation, we're thinking about rain, sleet, snow, hail. Precipitation here is different. A precipitate in a chemical reaction is a solid that we make as a result of a chemical reaction. So we can see here, and there are solubility rules that we can follow, and we may get into them later, but long story short, if we have two aqueous solutions, two things that are dissolved in water, they're going to combine in such a way that one of the products is going to be a solid, is going to be insoluble in water. That insoluble product is the precipitate. What we see here is magnesium sulfate reacting with sodium carbonate. Sodium carbonate is something that's used to soften water in areas with lots of magnesium and calcium deposits, like the Rocky Mountains, for example. They have hard water, which makes this film develop on all of their water that makes it hard to clean things. And so because of that film, they need to be able to soften that water and remove all of those substances. Okay, so got about 45 seconds here. So we see double replacement reactions when acid rain breaks down marble as well. Here we see a marble statue that's been broken down over the years by acid rain. And acid rain is another product of a double replacement reaction. So we have calcium carbonate, which in this case is solid, and it reacts with sulfuric acid, which is produced when certain things dissolve in water that are produced in factories. And it produces this soluble substance that causes the calcium carbonate or the marble to wear away. That's about all the time I have for this video, but I'll post another summary of this later on. Thanks for listening.